Unreal Engine 5 is an excellent tool for making video games, but often performance gets forgotten about with all the cool new features to make things look better. So today, we're going to talk about 5 more tips that can help you save performance in Unreal Engine 5. Last time we left off, I had kind of talked about sort of overall performance and why you should do profiling and optimization pretty frequently. And to kind of give you guys a leap into an example, down below you can find chapters for specific things that you want to check out. But just as an example, those last 5 tips and these 5 tips, how they've impacted my game alone. When I was profiling before I started, really diving into optimization, I was getting about 60 to 70 FPS. Sometimes it would dip down to about 30 to 40 when I was doing something very heavy, but it would go as high as about 70. After I've implemented a lot of the last ones and these ones, I did a standalone build, which is how you should always test when you're testing for the max FPS to kind of get an idea of closer to what your players are going to have. I was getting about 170 to 180 FPS, which is pretty bonkers. So just so you can see there, it's a massive increase, and that's why I always recommend people do it early, because a lot of these things are things that way you don't have to go back through and dig through each and everything and figure out what you did wrong. You can really nip it in the bud now. It makes it easier to play test. It makes it easier to push out updates whenever you're updating things for people who are testing your game. If they can actually run the game a lot better, they can give you better feedback instead of complaining about performance the entire time. If it runs well, they can give you actual feedback about the gameplay. So let's go ahead and jump into our first tip here, which is actually going to be using delays inside of for loops. Now, in C++, the way you do delays with things like that is not quite the same. There is something, I don't want to dive too deep into it, but there are things like coroutines. There are delays, but they're a little bit different than how you would use them inside of a blueprint. But specifically, I'm speaking from a blueprint point of view, because there may be times when you want to spawn things inside of a blueprint, and you don't want to write an entire, C++ function to do that, because there can be a little bit complicated depending on what you're actually spawning. And so let's just hop into that. And so when we're talking about spawning, specific things, I'm using an example of a projectile. So as an example here, I've got the spawn bullets delay function. What this does is when I call this, it spawns a certain number of projectiles based on my pool size I've indicated for object pooling, which we're going to talk about in a little bit. And what it does is it spawns those projectiles in sort of like an unactivated style state and basically assigns them to the turret that they belong to. And then from there, we go ahead and do what's called pooling. That's object pooling. That's to keep them from not really wasting as many resources as they normally would. And then we call what's known as a delay until next tick. So when you're running a for loop, it tries to run it as fast as possible. And so it tries to do things quickly. And as we know, in blueprints, for loops can be really expensive. They can be very performance heavy, trying to chug through whatever they're spawning. And so by adding that delay until next tick, what you're doing is you're giving the engine a little bit of breathing time. Basically, it calls the for loop, and it's that for loop hasn't completed that execution, and so it'll carry over another second. And what this does is your spike of performance, where you're spawning a bunch of things, then gets kind of flattened and made a little bit wider. So it does mean that you've got a longer width where performance isn't as ideal as you'd like, but that jump is a lot smaller, which means players are a lot less likely to notice it. Especially, you're running at 180 frames a second, it drops down to 160 for like 2 seconds versus spiking down to like 60. Players are going to notice a lot more of that big spike. And so with this delay until next tick, what this does is this just smoothens out any kind of for loops that you have inside of your blueprints. Is it the perfect solution? No, because you can do things in C++ that are going to be a lot faster and a lot more efficient. But this does help with when you have to do it, either have to do it in blueprints, or if you were someone who's a little bit newer, maybe has a little bit of hard time with C++. So let's move on to our next tip, since it's sort of related to this, and then it's going to be object pooling. And so what object pooling is, if you're unaware, is basically the idea that if you're going to need a lot of objects, rather than spawning and destroying them dynamically, which can be really, really expensive, you spawn them once, create a sort of pool of them, and then use them, the same items, over and over, and then you only respawn, you only spawn and destroy them as you actually need to. So as an example here, I have got what's known as a close-in weapon system, or CWIS. It is basically a point defense cannon that its entire job is to shoot down enemy missiles that are coming in. And so with that, I don't need my bullets to be unique. They're all identical. They're looking exactly the same way. And so what my gun does is it fires out these projectiles so that they react physically accurate. But when they either collide with something or they get too far away from the ship, I just pull them back to the original pool. So basically I just turn them off, turn off all the physics calculations, turn off everything about them, put them back in that list of items that can be drawn upon to spawn. And instead of my gun using a brand new projectile, spawning that in, taking up some game thread to spawn that in, it instead just grabs one of those that already exists, turns all of those things back on, moves it to exactly in front of the gun, and then starts it back off. It's a lot more performant of an option. What this does mean though, is that depending on the size of your object pool, it could eat into your performance, because if your object pool is too large, all of those things still do exist. Now they're in a much less condensed way, so you can get away with a lot more hidden objects, but it is something to kind of play around with, test. You will want to have probably a function that will create new ones and add it to that pool if you don't have enough. So if it starts firing and you notice that it's not going as far as it should be, so if your fire rate is too high or something and you're shooting off too many bullets and they're getting cut really short, you can add additional bullets so that they go all the way to their full length, or you don't even have to have them go all the way, but go pretty close. And that'll kind of help balance the two. All right, so now we're going to move on to our timelines versus material world rotation. So what is that? So in Unreal Engine, there are a couple of different ways to handle moving objects. Now, this is kind of a thing I've learned about recently, but there's something that you can plug into your world position offset using this function here, if you kind of want an example. So what this does right here, this function takes, there's two separate things. You can ignore the top one that plugs into the normal, but the bottom one, what this does is takes the object's position and it adds a rotational position. So basically I'm saying, here's where I want this thing to be. And then it plugs it into the rotate about world axis cheap. And then it takes the object's pivot point. So what this does is my mesh has a pivot point from my 3D modeling engine, and it gets brought into Unreal Engine. That pivot point, the engine knows where that is. And so what I do is in the material, I say my pivot point, I want you to rotate about that pivot point by this amount. And then it's going to return that in an X, Y, and Z. And then depending on what I actually take out of there, so I could take all three and actually rotate it in 3 different directions. But if I only want to do one direction, say like the X value or the Y value, I can rotate it with this material in this way. Now this works pretty well. The only problem is that if you are using the same material for multiple items, you're going to want to have it instanced and have a different instance per object. That way they're at, when they're at different angles, they can be rotated correctly. Certain ones, if they match the same rotation amount, you can have them be the same instance material, but if they're off at a certain angle, you have to use a different instance. Now this is really cool because this is very performant for doing a lot of things. It's especially something that, not this exact implementation, but something very similar for world position offset is used for moving large blades of grass. So like, let's say you got thousands and thousands of blades of grass. If you want them to move, it's much more performant to do it that way rather than physically actually rotating the objects in some kind of way. But there is a downside to this. It is a more complex option when it comes to moving smaller numbers of things and moving them more precisely. So as an example here, I have my player ship that has some what are known as radiators. Now these, what they do is they allow the spaceship to put out gas, essentially to keep it from getting it doesn't put out gas, but to keep it from getting overheated, it builds up heat in a heat sink. That heat is then pumped in a coolant liquid, which then is pushed to these radiators. These radiators then open up, and in space is an excellent medium for radiating out heat, just due to the fact that there's very low resistance. Now with that, what ends up happening is If you are rotating these, because of the different angles and all the different numbers that can go into these, it's a little bit harder to use something like a rotation material. Now it is possible, but it starts to get a little bit more complex and a little bit more difficult to do versus you do something like this timeline, and it's a little bit easier. Now timelines are not necessarily the most performant option. That's not to say that they aren't performant, but there are a lot of timelines can add up to be very unperformant. And so when you're using timelines, you need to think about, am I going to be using a different timeline for each and every single thing? Then I probably need to find a different solution than a timeline. But if I'm using one, maybe two timelines, and then having multiple values inside of that, it's going to be a lot easier. Now, there are a few different ways to use the timelines. The way I'm using it right now is I've got a set time, 5 seconds, that it makes these calculations. It goes from left to right. There are some really cool things you can do with multipliers that you can use a single timeline value to handle a bunch of different things. So for example, if I went from 0 to 1 and had like a gentle curve, I can reuse that curve by multiplying it by whatever I need. So as an example here, I go from 0 to 0.2. Now I do that 0.2 over 5 seconds. So that 1 second, if I take that 1 and I say divide that by 5, I can then get that value as it goes over that 1 second, but at a slower rate. Or if I increase the divider, I can get it at a faster rate. And that allows you to use a single value to get many different output values from the same timeline. So it's a little bit more reusable that way. And so with that, you've got a couple different things you can do with it. So example here, I've got a rotation and emission coming out of this timeline. And I've also used here as an example, I've got a timer by event here that closes this do once. So that way my 5 seconds, I don't have to worry about creating some kind of intricate timer. It's just literally a non-looping 5-second timer. Once it's completed, it resets the time, and I can change this at any time to kind of tweak how often players can open and close vents. Now, let's go ahead and move on to our next topic here. We're going to talk about UI optimization. So with UI, there are a lot of factors that come into play. Some of the big ones are going to be event-driven UI versus ticking UI. Now, event-driven is definitely the recommended way to go, and I definitely think it is a valuable way to go. But there are times when you're going to have something tick. Things like animations or things like that. I guess animations are kind of a bad example. A better example would be a value that updates frequently. With values that update very frequently, and you know that they will always be updating, always changing, you can sometimes get away with ticking. But event-driven means that it only ever changes if that value changes. So it is usually the more performant option. Now, the reason why that's important is because of things like canvases. Now, that's not to say you can't use canvases and that they don't have their own purpose, but canvases can be very expensive and they can have some inherent risks. So a lot of times people make the mistake of early on, they'll just have multiple canvases in a single widget, and they'll overuse them because they're thinking more about, this is a very easy thing to use, it's very flexible, there's a lot you can do with it, but canvases are also very expensive. So with that, you kind of want to focus on having things like overlays. Overlays are a lot cheaper. They do almost the exact same thing as a canvas, with the benefit of being not as expensive, and especially in an event-driven manner where you're only updating things every so often, overlays are just cheaper to use. So as we got an example here, this is all done with no canvases. That's not to say that you can't use canvas here or there, but currently I am not using any in this example, and yet it runs just the same. It looks and acts just the same as it would as if it was on a canvas. By full screen, it takes up the full screen. And so as you can see here, the benefit of the canvas is severely diminished in this capacity. And then the last thing we're gonna talk about here is going to be stat options. So I'm gonna link down in the description below. We have some actual documentation on using stat. So stat is a really handy little tool that I was kind of showing off a little bit last time. I went into some of the basics like stat FPS and stat unigraph. These are all super handy for diagnosing problems. See here, I've set up sort of an example problem. Basically, my GPU is rendering some shaders in the background, and so it sort of eats up performance out. It kind of diminishes a little bit, but that's kind of an example to show off how the stat system works. But yes, so with the stat system, we've got a lot of options here. In the description below, you'll see a full list of all the different commands you can have. For example, like stat AI, stat UI. They've got like a the normal stat FPS, stat game. In fact, let me kind of show this here. I shouldn't be affected by the fact that I got that other thing eating up performance. Game. And so with this, as you can see here, it's kind of showing off different performance. So you can kind of see, what is really taking up the most, performance here. Kind of give you an idea of what you should be paying attention to. Now with that, there's a lot of different things you can look at. The big thing to remember with stat is that with all these options, you need to make sure that you are looking in sort of a intelligent way. When you're looking at your stat graphs, when you're looking at all these different options they provide you, it can get a little bit overwhelming, and then you start to focus on a specific thing that you think might be the problem, but you're not getting to the root cause of why it might be the problem. As an example, I spent a long time looking at how to improve performance of physics in Unreal Engine because I kept seeing that physics bodies moving was eating up a lot of performance, and I was confused as to why I was having so many issues with, performance being eaten up. And I thought maybe it was a problem with the physics engine or with how I implemented some part of the physics engine with the ship moving, and I couldn't for the longest time figure out what was going on. And I got distracted. I wasn't paying attention to what my stats were telling me. I wasn't looking at all the different possible graphs that they gave me here, for example, like stat game and stuff. And so I spent probably a good couple of months trying to figure this out, thinking, my game's screwed because I focused so heavily on the physics being realistic of my game. And it wasn't until I took a step back and thought about it and realized that what was actually eating my performance wasn't, the ship itself. I took out my enemy AI and I realized my performance improved. So like, okay, that gives me a clue. What about the AI's eating performance? Well, I reload the AI and I'm like, okay, what about them as expensive? I knew that their calculations weren't very expensive, but just to check, I just removed all of their movement calculations, all of their decision making, and it was like, okay, that had little to no effect on the performance. So something else is eating it up here. And I was like, okay, well, there's not much here to pick from. So I'm going to go through a couple of classes that are attached to the ship, figure out what's going on here. And I realized that I have these CVIS cannons. And at the time I was doing object pooling and everything. But I realized that when I was doing my object pooling, I wasn't actually deactivating the physics calculations on these bullets. So they were sitting in the background, spawned all in one place, invisibly ticking on the physics calculator going like, hey, I'm colliding with something. Hey, I'm colliding with something. And then on top of that, I was spawning like something like 3,000 per turret instead of the 300 I originally intended to spawn. And so I had 10 times the number of projectiles. They were all calculating physics at the same time. I removed all of those, and instantly my game's performance doubled almost. It increased massively. That alone was enough for me to go, oh shit, that was the problem. And this is why I decided to make these two videos, is because I think there's something that not enough people pay attention to. When you are doing these profiling tests, when you're running through your stats, you need to make sure that you are actually paying attention to what the engine is telling you. Now, it can be made easier as they make improvements to the engine for you to figure out what it's telling you. But at the end of the day, the engine is telling you what the problem is. You just need to learn more about how to understand what the engine is telling you. It may not always be clear, and it may not always be easy. But definitely don't be afraid to ask questions, but keep asking those questions. Don't just assume that you found the problem just because you think that it's related to. Test that hypothesis. Try to figure out if that is actually a problem, or if something else is going on that you're not understanding in that moment. So that is it for today. That is all 5 of our great simple tips for optimizing an Unreal Engine. If you have any questions or anything else you'd like to see covered about optimization, definitely leave them in the description down below. Sorry, in the comment section down below. But otherwise, good luck, good hunting.